All right, guys. So first thing, sorry for the short notice change of plans on today. We realized at the last minute that the sections A and B, the schedule for section B had been swapped to put all the class activities on Friday, and so we discussed and decided we would do the same. So we're just flip-flopping the lectures, but the reading and assignment orders aren't affected because basically you don't actually need this stuff until Friday's assignment. But Friday we're going to be doing the in-class activity. So that's going to be, I'm going to split you guys up into groups of 4. Okay, I'll send out the groups. Well, I'll probably just put them up on the projector during Friday's class and work through a problem again for, it's going to be worth 10% extra credit on midterm number 2. So anyway, so today we're talking about the next step in applying conservation equations to control volumes. So we talked last time about conservation of mass. This time we're talking about conservation of linear momentum, which is more familiar to everyone here as Newton's second law of motion, F equals ma, however you want to state it. But what we want to do by the end of today is derived linear momentum equation, which we'll call LME for shorthand. This is a very short derivation, sort of like the continuity equation was. We want to understand how our choice of control volume affects the way we apply the linear momentum equation. And then finally, we want to actually apply that linear momentum equation to calculate the forces that are incident on a control volume. Okay. This is one of the single most, like this combined with the continuity equation from last time, are probably the most, say these are the tools I use most often when I'm doing fluids calculations. Okay, the LME is an incredibly powerful equation that allows you to calculate things like examples I gave before, or the thrust of a jet engine, the lift on a wing, the drag of an object moving through the air. Okay. So this starts out by recalling the definition of Newton's second law. Now we all suppose that we know and understand Newton's second law of motion, but if I went out on the street and I pulled somebody and I said, what's Newton's second law of motion? They would probably say force equals mass times acceleration. Okay. That's a little bit of an oversimplification. Okay, the real way that it is stated is actually that if we define P to be linear momentum, in other words, this is our mass times velocity, all right? Then what Newton's second law says is that the sum of the forces incident on a system is equal to the time rate of change of momentum of that system. All right. The reason this is meaningful, and the reason we can usually approximate this as ma, is that if we take the time derivative of this quantity, okay, what does conservation of mass say? It says that the time derivative of mass of a system is 0. So the only thing we end up with is basically mass times the time derivative of velocity, which is acceleration. Newton's second law. But we write it in this form because now this expression, the time derivative of something of a system, lends itself to this Reynolds transport theorem that we've developed. So in this case, we would say that P of a system, is equal to the integral over that system of V times little bits of mass, or
the integral over the volume of that system of v times rho dv. Okay, so the first step in applying conservation of linear momentum to something that isn't a system is to recognize or review or recall this idea that if we take a snapshot in time, at some instant in time, a system can be bounded by a control surface. In other words, we can we could say if this is our system at some instant in time, system, then we can place a control volume exactly coincident with that system. So at instant in time, system and control volume are coincident. That is, the contents of the control volume are the system, and the system makes up all of the contents of the control volume. The reason this is important is because if at this instant in time, when the system and the control volume occupy the same space, we consider the forces on a system, then by extension, the sum of forces on a system also is the sum of the forces on the contents of this control volume. So if we say, right, the system has forces made up of maybe weight, say we've got force 1, can be another force 2 over here. Okay. We can say the sum of the forces on the system is equivalent to the sum of the forces on the contents of the control volume. Oops. CV contents. Okay, so by extension, then, if we write Newton's second law, once again, we can say sum of the forces on the system is equal to, right, sum of the forces on the CV contents is equal to dt of the momentum of the system. Now we're getting into familiar territory. All right, we've established that we can write the sum of the forces on a control volume, again, a region of space, in an Eulerian sense. We take the sum of the forces on the control volume. We can represent it as the rate of change of momentum of the system inside of the control volume. And then the rate of change of momentum of the system inside of the control volume, this is becoming a mouthful, can be written out using the Reynolds transport theorem. So that's the next and really the final step in deriving the linear momentum equation is, right, if we write one more time the Reynolds transport theorem, right, CV, d dt rho b dv plus integral control surface rho b n dA. So we've got, right, the Reynolds transport theorem, and just as with the mass conservation, in order to write this in a form that involves our control volume and control surfaces, we need to pick variables to plug in for big B and little b. All right. Well, hopefully, just comparing, right, that guy and that guy right there, we can see that we need to define big B as the momentum of, or as just momentum, this quantity P. And if that's the case, right, so this is essentially, right, this can be thought of as our MV. And so little b, our intensive property, or the amount of big B per unit mass, then has to be simply the velocity. Okay? So now, substituting those into the Reynolds transport theorem, we get the d system dt is equal to the partial time rate of change over the control volume of rho v dv plus and then this, of course, be written as the sum of the forces on the CV contents. Okay, so this, what we've written right here, is the linear momentum equation. And this one always turns into a bit of a mind bender when you first see it, because of a few things. First, all of a sudden you're talking about velocity as being, right, the amount of momentum per unit mass. And so because velocity is a vector quantity, you've got a vector on this side and then vectors that fall out of both of these intervals. We'll deal with that in a second. This is actually a really useful characteristic. The second part, I'm going to walk over here so I don't have to in spaces. The second part of it that gets people kind of confused is the fact that you've got this v term over here and this v dot n, and people start to just kind of, they mix up their v's. This is velocity and this is velocity, of course, but think about it in different ways, right? Before, this was a little b quantity. This velocity here represents the amount of something per unit mass. Got it. V, the amount of linear momentum per unit mass. Remember, this v dot n represents the rate at which that quantity v is being carried across the control surface. So it's essentially, you're talking about the rate at which velocity is moving across a control surface, which means the rate at which that linear momentum is crossing the control surface. So it's a little bit of a meta thing when you think about the equation in depth, but it helps to recognize that that first v represents linear momentum, and that second v dot n quantity is just what I said. It's the rate of crossing or of transport across a control surface. So with that, we can write the interpretation of each term here, right? We've got the time rate of change of linear momentum of a system is equal to the time rate of change of linear momentum of the control volume contents plus the net rate of flow of linear momentum across control surfaces, right? And then right here, sum of forces on CV contents. Okay, a couple of notes. We're almost through with our definitions and derivations and moving on to examples here. But I mentioned that I would get into this idea that we're dealing with a vector quantity now, right? A vector equation. Before, with conservation of mass, it had exactly the same form, exactly the same kind of interpretation, but it was a scalar quantity, right? Mass is mass, regardless of what direction you're looking at it from. Velocity doesn't have that going for it, or momentum doesn't have that going for it. So really, this vector quantity, right, the p and the v's that go into your equations, as well as the f that ends up on the right-hand side of the equation, these all have components in each of the coordinate directions of your coordinate system, right? So if we say v, p, and f are all vectors, okay? In other words, all have, we'll say x, y, z, or, r theta z or r theta phi, right? Whatever your coordinate system, whether you're Cartesian, cylindrical, or spherical coordinates, each one of these quantities will have a distinct component in each coordinate direction. What that really means is that this equation can be split into scalar equations for each coordinate direction. In other words, so this allows us to split the linear momentum equation into scalar equations in, we'll just pick x, y, and z for now, stick with coordinate directions, or Cartesians. So for example, we could write sum of the forces in x, right, is equal to time rate of change of integral over the control volume of rho, the x component of velocity, right, which is going to be u dv, plus integral over the control surface, rho times the x component of velocity again, u v dot n dA, right? This is linear momentum in the x direction. And similarly in the y direction, just write this quickly, cv rho, we would plug in v, or the y component of the velocity. Now, this is another place where it pays off to think about, what the velocities that are being transported and then these velocities dotted at the ends really represent. We still have that vector v dotted with the n, right, the normal vector, because once again, that dot product comes out not as a vector but as a scalar, indicating the rate at which something's being carried across the control surface. So it doesn't matter what that something is. In this case, the x component of linear momentum per unit mass, or the y component of linear momentum per unit mass. All right, so let's go ahead and break out some examples. I think one of the best introduction examples to this concept is one of the examples in the book. And give me a moment, let me pull up these slides. Oh, are you kidding me? Go. Okay, so this is the example we're going to be discussing here. Essentially, if we've got some sort of a vane or a block, this is typical of turbo machines, okay, like water turbines and etc. But if you have a vane with a water jet that is spraying a jet in horizontally that then gets redirected by the vane through some angle theta. Okay, the question is, if we're given, the velocity v1, and if we were given the angle theta, can we figure out what the anchoring force in x and in y is necessary to hold this vane in place? Okay. So I have sort of a methodology that I like to propose for solving problems like this, or solving linear momentum problems. Sort of a step-by-step thing. I like to follow the template of, for steps, I can say 1 is basically select a control volume. 2 is draw a free body diagram of the control volume and the associated control surfaces. 3 is list the governing equations. 4 is state assumptions. And simplify the governing equations. And then 5 is solve for unknowns. And of course, as with any engineering problem, often when you list the governing equations, you might miss one. Stating assumptions, simplifying, trying to solve for unknowns, you might need to come back here, add one. These 3, 4, and 5 become a little bit iterative. But this generally holds as a pretty good procedural kind of way of working through problems like this. So I'm going to switch back over to the notes page. Okay, so our example, has this vane and this jet of water. And it's being redirected by the vane. Let me move this down a little bit so I have room to draw a control volume. Okay. And this thing is anchored to the ground. So step 1 is selecting the control volume. So a couple of rules of thumb here. Conservation of linear momentum. That's some of the forces that shows up. It basically that represents all of the forces acting on the contents of the control volume, exerted by things that are just outside of the control volume. Okay, so the contents of our control volume, for example, if we make our control volume look like this. This box. The contents of the control volume include the fluid as well as the vane itself. And so that some of the forces would represent the forces acting on the vane exerted by the ground below it. That's actually what we are looking for, the anchoring force on the vane, as well as any forces such as pressure acting on the surfaces of the control volume. The second thing that comes into play when we're dealing with selecting control volumes is thinking about the equation we're going to be solving in a second. We got that v dot n term, When dot products like that are usually easiest when the normal vector is parallel to the velocity, whether it's in the same direction or in opposing directions. So the best choice of control volume here is actually one that has the fluid crossing the control surface at right angles, anywhere that it goes in or out. So I'm going to suggest that we modify that control volume from our first choice a little bit by drawing it like this, okay? Because then that places our normal vector parallel to the fluid velocity, both at the left-hand side and at the right-hand side. Okay. Step number 2 would be drawing the free body diagram of the control surface, or the control volume and the control surfaces. So by that, I mean rather than drawing the vane itself, the beauty of control volume analysis is that we get to treat the control volume as a black box. So we're going to actually draw it as precisely that. Black box. There's our control volume made up of the control surfaces. What forces are acting on this thing? Well, we've been told in the problem statement. I wish I had a place to... I wish I could put different things up on the 2 screens so I could have the problem statement on one. But we've been told in the problem statement, right, to neglect gravity, so we're not going to worry about weight. We've been told to neglect viscosity, so we're not going to worry about any friction forces. Basically, we've got the forces that we're trying to find, okay? We've got the reaction force in the x direction, the reaction force in the y direction that are pushing on the vane. And then we have, wow, that's thick green. And then we have pressure forces acting on all surfaces, right? Okay, so in a case like this, we're going to see in a second that the pressure becomes unimportant. But in general, it's a good idea to account for the pressures whenever you're drawing your control surfaces, because often, well, a lot of the time, when you have things like jet engines, etc., that produce a very high velocity or something, they can modify the pressure at either the inlet or outlet. You need to account for that. But in a case like this, right, if we're told to assume that the pressure, that we have a free jet going in and a free jet coming out, okay? Free jets, the definition, as we established using the Bernoulli equation, is that they are at atmospheric pressure. So in other words, all the way around, we can assume that the pressure is atmospheric, which is going to mean that all of these forces basically cancel each other out, all the pressure forces. So cancel out because P atmosphere is uniform over the control surface. Okay, so basically what that leaves us with is, from the free body diagram, if we wanted to sum the forces in the x direction, we would end up with just the reaction force, okay, in x equal to, instead of ma, as we would write if we were doing dynamics, we're going to write that ddt of the x component of momentum of the system. And sum of the forces in y, which is only the y reaction force, is equal to time rate of change of the y component of momentum of the system. Okay, step number 3 is state governing equations. So in general, we're always going to rely on conservation of mass. Okay, conservation of mass comes in almost all the time. So that's the first governing equation we're going to invoke. mass conservation, which is basically saying that right, ddt of integral over the control volume of rho dv plus integral of the control surface of rho v dot n dA is equal to 0. And then we have momentum conservation, which is that dt of, that sum of the forces on the CV is equal to dt integral of CV rho v dv plus control surface rho v n dA.
Okay, so we're going to leave those written as is for now. We'll loop back to them once we've stated some of our assumptions and offered some simplifications.
Step number 4. Assume and simplify. It's like our engineering version of divide and conquer. So, assumptions, and for this, it would probably help if I could move this. If you guys need to take those notes. Man, this is really hard to. There we go.
Okay, so in the problem statement,
We've got water exits a nozzle with uniform speed.
okay, in other words, it's saying that the velocity that's coming out of the nozzle is constant across the diameter of the jet.
Right, so there's no spatial variation in the velocity. V is uniform, so write that down as an assumption. It doesn't say anywhere here that the flow is unsteady. Okay, so we're going to go ahead and propose that this flow is steady. We've got that we're neglecting gravity. And then we've got
Water, right? Basically, if we're dealing with water, that means the flow is incompressible, and we can treat rho as being a constant.
rho is equal to a constant value. All right,
So this allows us to do a few things, right?
the fact that it is steady, or first we'll say the fact that it is steady basically means we'll number these. Let's say we number these 1, 2, 3, and 4.
Our simplifying assumptions. I should have written these in a better order, but we'll take number 2 first.
The fact that it's steady basically means that we could cancel out the time derivatives
In both equations, right? Mass conservation and momentum.
the fact that we have a uniform velocity, right? That V is uniform everywhere it's going in or out of the control volume is very important, because that means that according to 1, these terms basically they don't change inside of the integral, right? They can come outside of the integral and act as constants. So let's quickly draw a little sketch again of our control volume. We've got normal velocity, or normal vector here, normal vector here. We've got V1 here, and we've got V2 here where it exits. I like to make a little table here that says, right, V1 is equal to what in our Cartesian coordinate system? Well, if we give it the magnitude of v1 without the vector sign, it's entirely in the x direction, right? Equal to v1I plus 0j. This means that v1 dot n is simply equal to negative v1, right? We're looking at this part right here, which signifies that this is an inlet. Looking at the outlet, well, what we assume to be the outlet, right? V2 is equal to, I should have drawn on here that we've got, right? This is at an angle of theta, okay? The V2 is equal to V2 cosine theta in the I direction plus V2 sine theta in the j direction. V2 dot N2 is equal to just V2, the magnitude of V2, right? Because they're pointing in the same direction. This is why it's really nice to have placed the outlet, that chunk of the control surface, perpendicular to the flow. Because basically that dot product just becomes a plus sign or a minus sign. And the reason this is great is because this term, this term, this term, and this term show up, right, here and here when we're dealing with the control surfaces. The final simplification we can make is that we've got, right, well-defined inlet and outlet. Which I should have included earlier, but this is going to allow us to split this integral right here into a integral over the inlet and an integral over the outlet portion. Okay, so we dealt with the fact that B is uniform, that this flow is steady. We'll come back to neglecting gravity in just a second, but then the fact that rho is constant, right, means that it also can be moved outside of the integral, okay, just like any other constant value. So that means that everything here, basically, can be moved outside of the integral according to points 2 and 4 in our simplifications. All right, so rather than scribbling all over the equations we already wrote, let's go ahead and restate them in our new kind of proposed simplified form. Simplified equations, right? Conservation of mass now can be written as the integral over control surface rho rho v1 dot cs in dA plus integral over cs out rho v2 dot n 2 dA, and linear momentum equation can be written as, and this is equal to 0, can be written as sum of the forces equal to cs in rho v1 dot n1 dA plus integral over the outlet rho v2 dot n2 dA. All right, so I halfway simplified these because now here's where we can say we've already figured out that v1 is a constant, v1 dot n1 is a constant, v2 is a constant, v2 dot n2 is a constant, which allows us to further simplify by moving everything that's inside of the integral outside. In other words, everything here is a constant value over the inlet area. and everything here is a constant value over the outlet area. So we can say rho v1 n1 a1 plus rho v2 dot n2 a2 is equal to 0. Which then, because v1 n1 is simply equal to negative v1 and v2 n2 is equal to v2, this becomes rho v1 a1 plus rho v2 a2 equal to 0. We can cancel out rows, and we basically end up with v1 a1 equal to v2 a2. Looks like our good old continuity equation that we used with Bernoulli, right? Similar approach to the linear momentum equation is going to get us rho v1 n1 a1 plus rho 2 v2 dot n2 a2 rho v1 negative rho v1 a1 plus rho v2 a2. Okay, we could also write this as Q, right? Basically, that V1A1 is equal to the volumetric flow rate. So we can recognize that this quantity is Q. And if we wanted to, we could rewrite this as V1 times rho Q plus, or negative V1 plus rho Q plus V2 times rho Q, where rho Q is equal to m dot, right? Density times volumetric flow rate. So a couple of different kind of simplified ways of writing these expressions, but at this point, we're now ready to go ahead and start solving for our unknowns. So the fifth and final step here solving for unknowns. First, before we solve for them, let's list what remains an unknown quantity, okay? Unknowns. We've got Rx and Ry, right? Those are the things we're really looking for. The reaction force exerted on the vane by the ground it's mounted to. That's our anchoring force. However, we also, in the problem statement, right, it says a jet with velocity of v1 and area of a1. So we'll assume v1 and a1 are known. Okay, basically those are given. We don't have numbers for them per se. But we're also missing. Oops. Basically, we're missing v2 and a2. Okay, those appear in both of these equations here. Now, what equations are we going to use to find these unknowns? You know, basically we're doing the number of equations, number of unknowns, making sure that we can actually make this happen. For the reaction force in X, we're going to be applying, right, the linear momentum equation, the X component. Reaction in Y will be applying the Y component of the linear momentum equation, right? So here's where the fact that this is a vector comes in handy, because we have an X component and Y component, and those are two different equations. Okay, so that handles two of our unknowns. For V2 and A2, right, we can relate we can tackle one of these using the continuity equation. Continuity or mass conservation. But we're missing one equation. Basically, we're not able to fully solve this problem that we're given. So we need one more equation. Something that can relate, for example, that we can use to solve for example, maybe the velocity, given the velocity at another point with known pressures. Let's think of it this way. If we've got our control volume, oops. Flow comes in here, it turns, it exits here. Let's say we've got a streamline with point 1, point 2. What equation would we use to relate the velocities between these 2 points if we know the pressures at both points? Bernoulli, right. So we're going to go ahead and invoke Bernoulli to give us one more tool to work with here. So this is where I say this is sort of an iterative process. You state your governing equations, you simplify them, you see whether you have enough to deal with your unknowns. If you don't, you've got to find another equation. So in this case, we can very quickly apply Bernoulli between these two cases, or these 2 points, by saying P1 plus 1/2 rho V1 squared plus rho G Z1 is equal to P2 1/2 rho V2 squared plus rho G Z2. Okay. Applying the same assumptions to this problem, to this equation here, we say we can ignore gravity, right? We already stated at the beginning of the problem, right, that at points 1 and 2, we have free jets. So the pressure is atmospheric, where the water's going in and where the water's coming out. So we can cancel out, basically subtract P atmospheric from both sides, and that would cancel out P1 and P2, because those are both P atmospheric. And so what we end up with is 1/2 rho V1 squared is equal to 1/2 rho V2 squared, which tells us that V1 is equal to V2, right? That the speeds of the flow going in and coming out are equivalent. Okay, so now we've got, so if we take Bernoulli, we say V1 is equal to V2. We plug that into our continuity equation, V1A1 plus V2A2. Then we get what? The A1 is also equal to A2. The jet is the same size coming out. So V1 equals V2 from the Bernoulli equation. A1 equals A2 from continuity. Okay, now we can plug the momentum conservation equation, or the linear momentum equation. So x component of the linear momentum equation gives us Rx is equal to U1 times negative U1 rho V1 A1 plus U2 rho V2 A2. All right, we're almost at the end here, so we're going to finish up just in time. So V1A1, V2A2, right, we've established that those two quantities are equal to one another. As we said, right, this is basically equal to Q, and then rho times Q together is equal to m dot. So we could write this now as m dot U2 minus U1, right? The x component of the velocity coming out minus the x component of the velocity coming in. If we go just up here a little bit and look at the x and the y components of our velocities going in and coming out, we can just substitute those values in, and we end up with now is m dot, right, v1 minus v2 cosine theta. We've established that v1 and v2 are equivalent to each other, so let's just use v1 is equal to m dot v1 1 minus cosine theta. Okay, and there's our reaction force in the x direction. Doing the same thing in the y direction, we would end up with ry is equal to, right, m dot v1, oops, right, v2 minus v1 be equal to m dot 0, sorry, v2 sine theta minus 0 equal to m dot v2 sine theta.